All right, so let's get started. So in the last lecture, we talked about the SRAM stability, and here is a quick summary. And we talked about the read operation. We need to be careful about this 0 to 1 disturb, right? We want to minimize the rise of that storage node voltage, which stores 0. So we have some constraints on the drivability of the pull down and cascade transistor. So you want the pull down to be stronger, right? Stronger pull down and weaker cascades. This is to satisfy the rate disturb requirements. And then we talk about the write operation. Then write initiated by the 1 to 0 transition. And then to make that happen, then we want stronger cascade, weaker pull up. So we talk about the static analysis and then the static noise margin, the butterfly curve. And then you have homework on that. And then we talk about the dynamic analysis. This is more realistic for actual operation, right? Because the noise will not be there forever. So in that sense, then the hold or the rate margin is underestimated in the static analysis, right? So actually you can tolerate a little more because the noise will not be there forever. But on the other hand, the write operation, the write margin is overestimated in the static analysis. Because in the real operation, your write pulse, which is the word line to be turned on, that duration is very short, right? That depends on the clock frequency. So you have to make sure that the word line is long enough, therefore you can flip the data. So here, any questions? All right, so then let's continue on today's discussion. So here are some design considerations for the SRAM bit cell design. And we talk about the rate speed. So at the cell level, what matters we discussed earlier. So for the first order, it's always like you discharge the bitline cap through the cascade rate current. So then this I cell essentially is this cascade, of course, includes the pull down transistor, which is like, two resistor in series. So the combined total resistance determines this I cell, and then C, the parasitic capacitance, CBL, times delta V, which is the voltage drop you want to develop between the bitline and bitline bar. So this is a sense margin, typically like 100 millivolts, 200 millivolts. Then you have the C times delta V, which is a charge divided by the I cell. Then you get the delay to the first order. So this is the rate speed, and one of the constraint is the CBL. And also here we haven't talked about the delay that the signal propagates through the word line, through the bit line. This is just for the delay that happens to this cell. If you think about the array, if your word line, you turn on the word line needs to, this signal needs to propagate through the array. And also when you develop the bit line voltage, this voltage needs to propagate along the bit line. So then the interconnect RC wire delay will also matter for the array level performance. So this depends on the array size, right? The larger the array, the longer the wire, then you have larger resistance and also capacitance. So the typical array size for SRAM, of course, depends on the levels of the cache, right? Could be as small as like 32 by 32. I mean, for the smaller size, could be not as large as maybe 256 by 256. So you can have different choices in between. But it's very rare to see the SRAM to be like 1000 by 1000. Okay, 1000 is 1024 by 1024. That is like 1 megabit. This is an uncommon to see SRAM who have such large size, because for that like 1000 by 1000 array, the interconnect RC will be too significant. The SRAM will be too slow in that case. So the typical range for the SRAM is like in this range. Okay, so just keep this in mind. Later when we talk about the DRAM and the NAND flash, you will see the array size will be much larger. Okay, so here when we talk about the array size, we are talking about the subarray. Of course, the total SRAM cache size, it may have many subarrays, but we are talking about the unit array. Like 1 unit of the array we call subarray. So this is a subarray size, typical subarray size. Okay, so then another consideration is the leakage current, because SRAM suffer from the standby leakage power consumption. Even you do not do any operation, you just hold the data, then you have the leakage path from the VDD to ground, right? VDD to ground. This is because those two transistors, one of that will be in off state. So the off current, right? For example, if this one is, let's say, 1, this one is 0, then the NMOS is off. There's no off current through the NMOS. But the PMOS is leaking. So the PMOS here, like VGS, PMOS VGS is from here and here, and VDS, both are VDD. I mean absolute value. We are talking about absolute value for PMOS because it's all active. So let's talk about absolute value. So it's all VDD. So the PMOS transistor, sorry, I made it wrong. Okay. So here, this is 0. This is 0 because this is VDD. And then PMOS VGS is 0. So even the VGS is 0, but the VDS is non-zero. Then you have the off current. Okay. The off current is due to the subthreshold leakage. So this I off is coming out from the power supply VDD. That will give you the leakage power VDD times I off. That is for this branch. And then you can do the analysis by yourself. And you will see that 3 transistors are leaking in the SRAM cell, in the hold state. In the hold state, I will not do that for you. Maybe it will be a homework or your exam question. But if you do that analysis, you will see that in the hold condition, 3 transistors are leaking, right? And then the leakage power will be VDD multiplied by the off current of those individual transistors. So that's why here the total off current will be those 3. Even you have 6 transistors, only 3 are leaking, okay? And then here is off current equation. I will skip that. This is to the first order, you know, is subthreshold slope stuff.
When you're holding, is bitline and bitline bar floating, or are they held at whatever was last used?
So normally you will pre-charge bitline and bitline bar to be VDD to make it ready for the next read operation. So your word line is off. So that's why it's hold.
Okay.
But then you want to pre-charge bitline and bitline bar to be VDD to be, you know, ready for the next read.
So that's why only one of the cascade transistors would be negated because the other one.
Yeah, exactly. Yes. Okay, so then the leakage power is a great concern for the SRAM. So that's why SRAM, if you look at total power consumption, so of course this depends on the activity ratio, right? So if you are not very active in the standby often, then the SRAM power consumption will be dominated by the leakage power. So that's why, for example, you are not using your phone right here in the standby mode, because you have the cache here, you have a large size of the cache. This cache holds some data there. the SRAM cache is leaking. That's why your battery is draining over time, even you are not doing anything. So this is the biggest concern for the SRAM, especially for the edge device, where standby is often, because your SRAM stores those data. You cannot power off your SRAM, because if you power off your SRAM, all the data are gone. So then, yeah, that's the problem here. Okay, so then let's continue the discussion for the speed. This is a new slide I added for this year. So if you look at the SRAM design for advanced node, the RC delay from the interconnect play more and more important role. So the word line and bit line RC needs to be managed. Okay. So here, if you look at the word line and resistance, so because you shrink the technology node, your metal 1 pitch and also the metal 1 wire width also shrink, right? For resistor, for piece of wire, the smaller cross section you have, the larger the resistance it is, right? So with the scaling, the wire resistance goes up. That means your RC delay goes up, right? So you have to manage that. So that's why in the recent technology nodes, when you look at advanced SRAM array design, so people will use double word line, okay? Double word line skin. So that means you're going to use different metals, for example, metal 1 and metal 2 in parallel to drive the SRAM array. Because one layer of the metal, right? So then the resistance is too high. So you have to add a parallel path, two resistors in parallel, the resistance will be lower. So you use more metal routing to compensate for the increase of the resistance. So even for the latest technology node, I think even triple word line has been proposed. You use 3 metal layers to minimize the resistance. And also for so here some data, I think this is from TSMC. At the 7 nanometer node, you see that the wire line resistance without optimization is like this. It keep increasing with the technology node. But if you do the double wire line, then it will bring back the resistance. And also for the bit line, I think they use some fly-in bit line skin, which means use upper metal layer to reduce the bit line cap. So use some upper metal layers. So here, with those 2 skin, you see that the waveform become better. So basically the word line pulsing, right, become sharper, and also the bit line discharge will be faster. So that will help with the sensing speed at the array level. So the SRAM design today spend a lot of effort on those parasitic optimization at the array level, at the interconnect level. Okay. And then we talk about the leakage, the standby power consumption. So here are also some techniques proposed to reduce the leakage. So let me quickly talk about that. So here, this was proposed before for some older technology node. So that's why the VDD is high, but you can use the same principle for more advanced nodes. So here, if you look at the conventional standby skin, as I just said earlier, so here in this case, VDD is 1.5 volts, okay? In this example, for older technology node. As I said earlier, so in the hold mode, bit and bar both are charged to be VDD. In this case, 1.5 volts. So if you analyze a transistor, look at the bias difference between those terminals, let's say gate, source, drain, then you will see some of those transistors will suffer from different kinds of leakage mechanism. So we only talk about the I-off in the earlier slide, which is this one, this gray one. This is a I-off, okay? So in this example, those three transistors here, here, and here will have that I-off, okay? In addition to that, there are other mechanisms for leakage current. For example, this red one called GIDL, gate-induced drain lowering. So this is called Guido current. And Guido current, we will maybe talk about more physics later. But here, what you need to know is that Guido current happens in this condition. When your VGS is negative and the when the VGS or VGD is negative. So basically your gate potential is lower than the source or the drain. That's for NMOS, okay? Then that will have the Guido current. Or let me show you what is Guido current. If you still don't understand what is Guido current, then I will draw some IDVG for you. So let's say ID versus VGS in the log scale. What we have is this one, right? So this is your threshold voltage, and then this is a subthreshold slope we discussed before. So this is not a full picture, okay? If you draw this IV curve along the negative side, when VGS is negative, this is for NMOS. What you will see that is you have the increase of the current on the negative side, okay, when the VGS less than 0. So this is the Guido current, which is higher than the I-off actually. So this is this GIDL Guido current. We'll talk about the physics more later maybe, but basically it's due to the band-to-band tunneling from the, let's say, the drain to your channel. So if you look at the bias condition of those transistors, you will see that many of those transistors are under this Guido condition. So you have additional leakage, okay? And then here, it also has this orange one, which is basically just the gate current, IG. So this one is not very important for today's transistor, because this one is minimized by the high K metal gate already. So previously, when you have the poly gate, when you shrink the SiO2 thickness below like 2 nanometer, you have direct tunneling from the gate to the channel. Then this becomes important. But in today's, I will talk about high K metal gate in the following slides. So if you use high K metal gate, the gate leakage current is negligible, okay, today. So this one is not very important for today's transistor, okay? So here we have a different like a bias scheme for the hold operation. And you asked the question before, right? Normally you will do this VDD, right, for the beta and beta bar. But if you bias the, let's say the beta and beta bar in the hold condition somewhere in the middle, let's say 1 volt, and also you raise the ground level VSS above the real ground to be like 0.5 volts. You can look at all the bias condition here. Previously, you will see like 1.5 volts between those terminals. But if you do the analysis on this circuit, you will see that the maximum voltage will be reduced to 0.5 volts across those terminals in this example. That will help reduce many of those leakage by the bias condition optimization in this case. Okay, so just some idea to reduce the voltage difference between those terminals during the hold.
Is it more common to bring VSS up or VDD down?
So you can bring the VSS up, I think. Yeah.
Is this being considered as a dynamic voltage scaling?
No, this is not your logic chip. You have the DVFS. So here is just in the memory hold condition, you have different bias condition. Yeah. Okay. So then also you can do something differently if you have different transistor VTH, right? So what you can do is, let's say for the latch in the middle, because you know the leakage current goes through here, VDD to ground. You have two transistors suffer from that, from each branch. So you can use some higher threshold voltage, which means lower leakage current for those transistors in the middle. And then for the pass gate, because you want to, access the data fast during the read or write, so you use some normal low VT transistor there. So here are some plot to show that if you do that, then you can improve the noise margin and also reduce the leakage. So there are many ideas you can play with. Of course, not every technology node you can do, this kind of change, depending on the, foundry's offering, whether you can change things or not. So I would say in more advanced node, you have less flexibility as a designer to change the SRAM design, okay? Because SRAM design is optimized by the foundry already. Then you will have less flexibility. So I should say this way, okay? Foundry will optimize the SRAM cell for you, and you just use memory compiler and call and let's say design an array of the SRAM cache directly with high level, description. Of course, you can handcraft the SRAM cell by yourself. That means you lay down the 6 transistor manually and do fully custom design. If you are taking the other course, 6130, advanced VLSI, I think that's one of the projects there. But that is not optimized, okay? Because you have to follow the logic design rule. If you hand make your SRAM cell. So, I mean, for the real chip design, you have to use foundry rule, okay, for the SRAM array, which is highly optimized using a lot of design techniques. Okay, so then let's talk about the SRAM layout. So here is a history of the SRAM cell layout evolution. So in the early days, let's say above 350 nanometer node, then you may not have 6 transistor SRAM. At that time, you may have like this so-called poly node 40 or polysilicon TFT SRAM cell, because at that time SRAM is expensive in terms of the area. So I will show you what that means in the next slide. But below like 250 nanometer, 6 transistor SRAM becomes the mainstream. And there are many like advantages doing that because it's fully a CMOS logic. You have the real-to-real operation. And then we will show you the layout changes over the technology nodes. So this is what I mean. The transistor do not be 6 transistor. So for example, here you can have 2 polysilicon resistor as the load. It's like you have the like a resistor load instead of PMOS node. So it's still functional as SRAM, but you may not have the real-to-real operation because here this resistor will always have some voltage dividing effect. You cannot turn off the resistor, right? You can turn off the PMOS, but you cannot turn off the resistor. So then this does save some area, right? Because the poly resistor can be, fabricated on top, right? You do not spend the transistor footprint. And also in the old days, you may not have the PMOS technology, right? Then you have the pure NMOS design. And of course, you can have the NMOS between the depletion mode and the enhancement mode, which means the VTH of the NMOS could be negative. Then you can use that as a node. But again, those are ratio logic. It's not like a, real to real. And also you have always have the large leakage path from the VDD to ground. So that's why today the 6 transistor SRAM cell becomes the mainstream. Okay, it's like a CMOS logic becomes the mainstream. So we talked about this before. What is truly scaling, right, over the technology nodes? It's not the physical gate length anymore, right? What matters on the horizontal direction is the CPP, contact poly pitch, or contact gate pitch. So you are looking at the center of the source to the center of the drain contact, and then you hope this CPP is scaling, which is true. From 130 nanometer down to 20 nanometer, you see LG does not really scale too much, but CPP keeps scaling. So the contact size shrinking, and also the spacer, which is the distance between the gate to the contact, is shrinking. So those reduction help with the CPP scaling. Okay, so this slide is important. This slide is important because 6 transistor SRAM cell, let's say layout design, even for today, advanced node, looks similar to this one, okay? So there's no change on the overall layout over the past 30 years already. So here, this is for planar, let's say 28 nanometer design. So what is important here? I hope you should have this capability because it may be in your homework, maybe in your exam to look at this layout. You need to understand which is which, okay? Basically, question is, let's say, where is the pull down? Where is the pass gate? Where is the pull up transistor on this layout? You should be able to locate that. Okay, let me ask. Where is the pull up? Any idea?
The one connected to the VDD.
Yeah, the one connected to VDD, that's good catch because PMOS attached to VDD. And also you need to notice that here NVL is reserved for PMOS, right? So the PMOS is in the middle, okay? So it's symmetric. 3 transistor to the left, 3 transistor to the right. And then here, this is a PMOS transistor, okay? Basically, this is a PMOS transistor VDD. You need to create this one with the, let's say, with the schematic, right? I think this is important for you, okay? You want to create this layout to the schematic. So this is a pull up PMOS here. So here it says gate, right? This green one is a gate metal. Or maybe in this case it's polysilicon. So here you have this contact with the VDD, and then if this is a pull up, then where is the pull down or pass gate? So here you have 2 more transistors here, basically. My question is, which is pull up, or which is pull down, which is pass gate? Pass gate is bottom, okay. Then this is pull down. Why this is pull down? Because pull down, you see here, right? It's inverter, right? They share the same input, the same gate. So that's why this green line, control both pull down and pass gate. And then where is the storage node? Where is the storage node? This is a storage node, okay? This is your pass gate. Pass gate attached to this storage node. And then this is VLAN that controls the pass gate. This VLAN controls the pass gate. Okay. So then the question here is, if we really want to have this F square stuff, then how many F square? So I would say this is it's not a good definition, but let's still assume the F is the same as a tech node. We discussed what is really scaling, but let's say for the normalization point of view, let's have the F the same as a tech node, okay? It's just a way to normalize the area into the F square, the unit area. So the question here is how many F square for this layout? So here on the horizontal side, we have 5 metal 1 pitch here. Why? Because here you have this contact. Oops. Okay, between those contacts, this contact will attach to your metal 1. You have 5 metal 1 pitch. And then on the vertical side, you have 2 CPP. Why? This is the source and drain of the transistor, right? You have 1 CPP and then another 1 CPP here. So by the way, so the layout here I show here is like rotated by 90 degrees if you compare to the what we showed earlier for the logic standard cell. Logic standard cell, when we showed earlier, the CPP is on the horizontal side, and the vertically you have a few number of metal track, right? But for the SRAM, we just rotate by 90 degrees. It's the same thing, but here the metal 1 is on the horizontal side and CPP is on the vertical side.
So in this example, the ratio of PU to PD to PG would be 2:1:1.
Oh, yeah, I haven't got that point, but you mentioned that. Yes, I actually want to talk about that. Yeah. So since you brought up this, so then a question for you, right? From this layout, can you tell this ratio, right? So yes, here you see the pull down is wider, right? This is a W, and this is your L of the transistor, right? W over L in this case is 2, and then you see the pass gate, which is narrower, right? Because this W is 1, and then pull up, this is 1, so 2, 1, 1. Okay.
Once again, explain what M1 pitch is for example.
From this contact, you see this contact. This contact needs to be separated by the M1 pitch. Because that contact may connect it to your M1. Of course, some of them may go to M2 for the routing purpose, but they have to first go to the M1. So here, I haven't finished that. So here, I want to say that M1 pitch is roughly the same as the CPP and M1 pitch. And then for this design, it's roughly 4F. Okay, if you really use F as a technology node, if you look at the older technology node, for example, the Intel like 22 nanometer, if I recall the CPP is 90 nanometer. 90 nanometer and the 22, 22 times 4 is roughly 88, which is close to 90. So I would say what really matters is the CPP and the M1 pitch. This is something that is defined by the design rule. And then it happened to be around 4F if you use F the same as the tech node, which is meaningless. But if you do that, then the CPP and M1 pitch in the SRAM design is roughly 4F in the older technology node. I mean, older is like a 65, 40, 28, 22, around that, okay? This is generally true. It may not hold for today's advanced latest technology node because the design is very different. But in the bulk, let's say in the bulk planar SRAM, like 65, 40, 28, this is good. Okay, so if you do that, the cell area is 2 CPP times 5 metal 1 pitch. So roughly it's 10 CPP square. And if CPP is 4F, then you get 160 F square. This is generally true for high density SRAM cell size. Of course, you can enlarge the W over L, let's say for faster speed. For your lower level cache, like L1 cache, you may have like 4-2. Here you may have 4-2-1 or something like that. Then you may get like 300 F square in terms of the area. But the smallest one you can get is roughly 160 or 150, 160 F square. Okay. Any other questions on this slide? This is a very important slide. Okay, so then let's look at some layout that is at even older technology node. Let's say above 90 nanometer, let's say 180 nanometer. You may have the SRAM cell layout like this. So what we showed before is like this one. It's called wide cell. Okay, this below 90 nanometer. This is widely used. It's called wide cell because it's wide in this horizontal space. And then previously it may have this tall cell because it's tall in the vertical space. So here, my question is, okay, if I give you this tall cell layout, can you figure out which is which, right? Where is the pull up? So I won't do it here. You can practice by yourself, but a few hints. This dash box is unwell, so that means the PMOS should be somewhere here. And then PMOS should share the same gate as a pull up and pull down should share the same gate, right? Then that is how you identify which is which. You can always use that principle, right? First, look at where is the PMOS, and then where PMOS, and then second, which one shares the same gate with PMOS? That is a pull down. Okay, so here for today's SRAM cell layout is always this wide cell because below 90 nanometer it's very difficult to pattern something like this because you have like this wires like a T shape. You have both horizontal and vertical wires. So it's very difficult for from the patterning point of view. So you want everything to be very straightforward and simple. So you always have only like horizontal wire or vertical wire. Then that will help with the lithography. So all the gates should be oriented in the same direction. All the channel should be, source and drain should be either horizontal, or if vertical is all vertical. So previously here you may have vertical and horizontal channel. So that is not good. Okay. So you want simplified pattern for lithography. So here are some like real example. This is from IBM, I believe, 45 nanometer. So this is a real layout from whatever, EDA cadence, for example, right? If you look at the layout, it may look something like this. And then this is a real design for this particular technology node and particular process, it has all those design rules, which may violate some of your logic design rule because the foundry optimize those distance from the gate to the contact to the diffusion. So it's custom design. But if you look at the general layout and orientation, it's always something like this. Okay, always. So let me spend a few slides on the lithography, which is related to the fabrication. So the SRAM patterning is to follow this regular pattern because it's more and more difficult to, pattern this kind of shape using lithography. So if you have some, knowledge about the device fabrication, then, for the mainstream lithography, for many technology nodes, is based on this 193 nanometer lithography. This 193 nanometer is the wavelength of the light. It's already UV light in 193 nanometer because of visible light, is from 400 nano to like 900 nano. Below that is UV. From the basic optics, right? So the resolution is roughly, half of the lambda from your basic, optics, if you consider the diffraction and so on. So in principle, like 193 nanometer, like lithography, then you can only pattern maybe 90 nanometer feature size. But there are many other techniques introduced by the industry to continue the 190 nanometer lithography to more advanced node, even for like maybe 14 nanometer, 2214 is all based on this 193 nanometer lithography. There are many in technique. For example, they increase this numerical aperture using some, immersion lithography technology. So basically, here between the lens and then the pattern, you fill in some liquid, some kind of oil, which have this refractive index larger than 1, which will be divided by this larger than 1. So if it's air, it's a vacuum, or air is like 1. But if you have some dielectric liquid in between, you can increase this value. So you can decrease the resolution, like the feature size. And also, this OPC is widely used for this computational lithography. So what that means, so for example, here, if you do nothing after the patterning, even though from the layout, right, from the layout is all like a straight line, right, like a rectangle. But due to this, refraction, diffraction, all the optics stuff, after the patterning, then the photoresist may have the round shape at the end. Okay. So this OPC is to predict what will happen after the lithography. Therefore, when you make the mask, it will compensate for this. For example, when you make the mask, your mask may have a small like end, right? Your mask may be something like this. Even though your layout, okay, will be something like a rectangle, but when you transfer the layout to the foundry, when the foundry makes the mask, they will do this OPC and then proactively, design something to compensate for this distortion after lithography. Okay. Oh, by the way, so here this is a SRAM, and again, those are the what is this? Okay, my question. Right. You need to create the TEM image. This is under TEM transmission electron microscope. So this is that one. This is this gate pattern. So anyway, so this is OPC. And then if you do that, and then it will help. And also the double patterning or multiple patterning is introduced. So I will talk about that in the next slide. But if you do that, then you can get a very good pattern like this. Of course, for today's sub 7 nanometer node, industry switch from this 193 nanometer to the EUV, which is made by ASML. So EUV is extreme UV, and it has the wavelength around 13 nanometer. So that's why it's useful to make a very small pattern. But before the EUV become like a mainstream, industry has created very innovative method to do the patterning, even with older lithography, like wavelengths. So here, this is double patterning. So the idea is that it's very difficult. This is again this pattern you want to have. You have some gap in between those wires, but if you directly pattern this, due to the optical, this diffraction stuff, then you will easily get this round or whatever, distorted shape if you do one lithography step. So that's why it's used like double step. So the idea is that during one lithography exposure, you only pattern along one direction. So for example, here you first only have the horizontal patterns in the first step. And then in the second step, you have this vertical cut by the mask. And then you cut this. So then you will have better shape. And also you can use this spacer technology to pattern small features. Actually, this is the old way that the university makes the FinFET. We will talk about the FinFET technology later, but in university, even 25 years ago, when UC Berkeley, Professor Chen Minghu's group made the first FinFET, because university will not have advanced lithography tool. How do you make a small FinFET? So this is how it works, okay? So you first get some pattern, notch pattern, using conventional lithography, and then you deposit something, which is like the screen layer, cover this step, and then you etch those green stuff, like dielectric, you etch it away. But then here, because it will be like will etch only the surface. So on the side wall of this step, we call spacer, you have some leftover of this material. And then you etch away this like dummy step. So what is left is this sidewall or this spacer, which is only a few nanometers thick, because you can define how thick you deposit this green material. So use this as a hard mask to further etch down the silicon. If this this purple one is a silicon, then after you use this as a hard mask, you etch the silicon. Then what you left over here will be a piece of silicon fin. This is a FinFET.
So that the green is with photolithography, and then everything else is just chemically etched.
So your photolithography defines this pattern, this notch pattern, right? And then the green one is by deposition, right? By deposition and etch. So that is more controllable in terms of the nanometer, right? So you can let's say deposit maybe 5 nanometer thick green material, and after that you will have only 5 nanometer in this direction. So this is a poor man's method to But even, I mean, here at Georgia Tech, we can do this. I mean, in our clean room. If you want to really want to make a small feature. It's not easy, but it's doable without advanced EUV. Okay. So then let's talk about the lithography. So as I said, so you have the many like techniques like immersion and then double patterning and OPC to extend this 190 nanometer, 193 nanometer lithography. But in today's advanced technology node, EUV is widely used below 7 nanometer. So this is the evolution of the lithography. All right. So then any questions before we move on? So next we will talk about some scaling challenges for the SRAM. Lithography, of course, is one of the challenge, but there are many other stuff. So here, let's look at the cell size scaling. And this is till the 22 nanometer. This is from Intel. And here, this is the image. So you need to look at this kind of a TEM image, okay? And you see they have the same pattern. Again, this is similar to the layout we showed earlier. But you see that at 45 nanometer, actually the pattern become more regular because of the, this OPC and the double patterning introduced. And then you see the shrink of the cell size. This is a 6 transistor SRAM cell size, right? So here at 22 nanometer, it's below like 1.1 micrometer square. So the SRAM cell size scaling from this planar to the FinFET 22 nanometer, then follow the Moore's law very closely, like 0.5x reduction every other year. This is the good time for the SRAM scaling. And then even we extend the plot to 14 nanometer. So this trend will maintain. So here you are looking at SRAM cell size, which is blue dot, which is micrometer square in the unit of micrometer square, which is on the left axis. And then, as we discussed earlier, what really matters is the CPP or CGP scaling and also M1 pitch scaling. So you see that this one, the product of those two will eventually determine the SRAM cell area. But of course, you see a little bit like a flattening of the CGP in the recent nodes. So that's why you are seeing some deflection here. So this is what I did this year. So I just add a few more data points for the latest technology node. So what I added here is a 5 nanometer and 3 nanometer node. And those two numbers are from TSMC, N5 and N3. So you see that it almost saturates the scaling. And here are the typical numbers in terms of the cell area. You can refer to that. But I want you to remember this number, about 0.02 micrometer square. Or in other words, it's about 100 nanometer by 200 nanometer. It may not be exactly like 100 by 200, but I just want to, have the product to be 0.02 micrometer square. So if you think about the size, it's about 100 by 200, something like that. That's the latest SRAM cell size, high density SRAM. We are not increasing the W over L. We try to use minimal sizing.
For minimal sizing, would that be L2 or L3?
L3 cache, right? Minimal sizing, yeah, high density HD cell.
Child like mentioned that if we incorrectly assume F as the techno, so in general, like based on the homework that we have seen that F in general has been assumed as techno, but how low can the value of F go?
So that's why F is becoming meaningless, right? When I said here in this region, if you normalize to F squared, if you still use F as the same as technology node, then if you normalize that, we see that it's 160 F squared. But here, because it's not following this trend, if you normalize here, if you use F 3 nanometer, then SRAM cell will become, I did that, actually it's more than 1000 F squared. Because F loses the meaning, right? But if you still use F as a normalization unit, then you get more than 1000. So what matters is this number, the real number. What matters is the real number. That's why I want you to remember this number, 0.02 micrometer square for today's 5 nanometer, 3 nanometer SRAM cell. Okay. So here, then the challenge is the SRAM mismatch due to the process variation. So we showed this butterfly curve before for the read condition. And if you have the mismatch, let's say those transistor, VTH, the left branch, right branch do not match, then you will have this distorted butterfly curve, and then your SNM will be the smaller one, right? So if you measure many cells in the array, this open window will become smaller and smaller, right? Because you have to make sure the entire array works. So as you scale down, you see that statistically you get more and more variations, and then the SNM will become smaller and smaller statistically. So this is another challenge we have to manage for the advanced SRAM cell design. The variation or variability is a big concern. And also, when you decrease the power supply voltage, right? This is the same technology node, but you decrease the power supply, let's say from 1.1 volts down to 0.7. So you see that this open window is almost gone. Because at lower supply voltage, the read margin keep decreasing. So this variability is a big concern. So we're going to spend the rest of the lecture to talk about the variability in the transistor. And there are many intrinsic parameter fluctuations in the transistor structure. So here, this is a conventional planar buck MOSFET. And this is in cartoon figure. And everything is perfect here. But in reality, it's not like this. This is what really you have on the chip. So those edges may not be straight as you defined in the layout. And also the dopant will not be continuous as you assume in the ideal case. The dopant, right? For example, you have the, let's say, the boron to dope into the silicon. So the boron atom will be scattered somewhere in the channel. So it may not be a big deal when the transistor size is large, because you have many of them. You can average out the effect of those discrete atoms. But as you shrink the technology node, then the total dimension here is very small. So you only get like tens of atoms, dopants there. Then the exact location will matter. And also we'll talk about the work function variation. So there are many non-ideal effects that will impact the VTH and also the on current, off current, all the parameters of the transistor. So that's why here, if you measure the SNM, right, as you shrink, your SNM will have wider distribution due to the variation. So here I summarize the primary sources for the variation. So I would say the first three is more spatial, and then this is more temporal. Spatial means mismatch. The transistors are different from each other, even within the die. Of course, from die to die, across the wafer, you have the global variation. But even within the die, even within the SRAM cell, the left branch, right branch, the transistors are different due to this random dopant fluctuation, RDF, and this non-edge roughness, LER, and the work function variation, WFV. So this will result in the VTH, I-on, I-off variations. And also here we have temporal variations, like this random telegraph noise, RTN, and this BTI, especially for the PMOS and BTI. So those will make the VTH change over time. Delta VTH over time. This variation between cells, this is between cells. Temporarily, even for the same transistor, the VTH could change over time. That means your SNM is not a static number. As time goes by, you may have different noise margin. So those are the major effects. So let's talk about one by one. So random dopant fluctuation. So this is how you look at the dopant. Okay, let's say the red ones are the dopant. So you may have hundreds of them inside the channel, but as you scale the technology node, you may only get like dozens of those dopants in this small dimension. So that will give you the variation of the threshold voltage. And to the first order, this sigma of the VTH due to the RDF is given by this formula. And then what matters here is COX is the gate capacitance, NA is the doping concentration, WDM is the depletion width. And then what matters is this L and W, that is your gate area. Your gate area. So if you plot this, right? So here as we shrink the channel length from let's say from your 250 nanometer node to 32 nanometer node, the number of dopants may shrink from 500 to only like maybe 20, 30 dopants in the channel. And then that will increase the sigma VTH to like more than 60 millivolts. So why this discrete dopant will impact the VTH? So let's look at some examples here. The location of the dopant matters. Why? So if the dopant are scattered, basically you need to understand what the dopant does for the band diagram. So basically you have the band diagram, right? Source and drain. You need to maintain the PN junction, right? If you think about the PN junction, let's say your source and drain gate, right? Your PN, NPN. If you have a dopant, P-type dopant in a channel, right? Effectively, you are going to create this PN junction, so you can have this barrier. So that's why electrons, will be flowing over this barrier. And we discussed before, when you apply gate voltage, you are going to lower down the barrier. Therefore, the electrons can flow over. So what matters in the leakage, in the subthreshold region, you want to maintain this barrier here. So if you have the dopant everywhere, then this is along the W direction. This is L. So if you have the dopant everywhere, so then you can maintain this barrier across the width of the width direction. But somehow, if you're unlucky, or you're, let's say, dopant here, and here you do not have much dopant, then you will only have the barrier here, but in here you will have very flat potential. Then electrons can easily go through. That means you have larger leakage, or let's say your VTH is smaller, right? So depending on how those dopants are located. First of all, how many of them are there? Second, how they are located. So different transistors, because it's dopant injection during the fabrication is a random process, right? You inject the dopants, but you really cannot control where the dopant is located once you inject from the source. So here, if you measure statistically, you will have, different VG, a different VTH, and different on-state currents. So here, sample A and sample B. Of course, this is bound by TCAD simulation. So you can correlate this data point with this kind of potential or current, depending on the dopant location. You may have dopant here, 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 but not here. Therefore, you will have a leakage path. You have a low VTH compared to this one, where you can cut off across the entire channel. So here in this RDF, so this pegron plot is widely used. So what is that? Because of this formula, what you can do is to plot the sigma VTH measured from many transistors as a function of the transistor's gate area, but 1 square root of the gate area. So 1 square root of the gate area, which is this guy. So if you do that, then you have this slope, which is basically the coefficient of the others here. So the RDF will give you the straight line, but then in the smaller cells, you will see that the measured data will deviate from the RDF, like prediction. So this is due to additional variation sources, additional other variation sources beyond the RDF. So what is that? So let's look at the LER. So the line edge roughness will give you additional variation. So LER, this is when you pattern, right? This, we talk about the lithography. So even the mask, after the patterning, you have a very straight line. After the, let's say, edge, you may not get the straight line along the edge. You have some roughness of those wires. So this is due to several reasons. One of that is due to the photoresist. Because when you do the lithography, right, first you have the photoresist, which is polymer. And then you shine the light. Then under the mask, let's say the polymer is preserved. And then outside the mask region, then you can dissolve those polymer in some etchant. So because the polymer here, this photoresist, have this molecular structure. So the edge, if you look at the edge, will have a few nanometer like roughness due to you miss one molecule there, or you have additional molecule there. So the edge will be rough because the molecule there is a few nanometer in diameter. So you will get this kind of rough edge from the photoresist, and then use the photoresist as a mask to etch whatever pattern underneath. That roughness will be transferred to your real structure of the device. For example, if you pattern a metal wire, that photoresist roughness will be transferred to the wire edge, like your metal one wire edge. So that's why if you look at under the microscope, if you look at the edge of the wire, it always will have like a few nanometer variation on the edge. It may not be a big deal if, let's say, the line width is large. For example, if you pattern a large wire, let's say 200 nanometer in width, you have like 2 nanometer variation on the edge. It's just like 1% variation. May not be a big deal. But for advanced node, your wire length or wire width, reduce to like 30 nanometer. If you have 2 nanometer variation, it's like already like 15%. So here, this sigma of this LER will always be the same because of the molecular nature, right? No matter how wide the wire is, the edge is always rough by that 2 or 3 nanometer. If your wire is large, like 200 nanometer, not big deal. But if your wire is small, like 20, 30 nanometer, this 2 or 3 nanometer difference will show up. So if you think about the gate length, right, because your gate will be patterned, your gate edge will be rough. That means effective LG will be different for different transistor. That give you additional variation source. So any questions here? So this is called the gate LER. If you think about the gate edge, it's rough. All right, I think time is up, so we'll stop here. Okay.